fantastic. Just another, okay, the full screen. Okay, share. Okay, share this one, share, and then I should be sharing. Are you seeing my presentation now?
Perfect, you can.
Can you
Yeah,
see
yes,
it?
perfectly, you can
Yes,
start.
yes.
Thank you.
Ah, okay. Okay, good. Okay. So thank you, Antonio, for the nice introduction. So yeah, I come from the Telecommunications Institute in Aveiro, Portugal, and I've been working with diamond for almost 21 years now. And I'm going to talk to you a bit about the electronic applications that we are pursuing here in Aveiro. So, brief outline of my talk. I will introduce you to the properties of diamond. Then I will tell you how we can fabricate artificial diamond. Then I will go into more detail about the types of diamond films. And finally, I'll go through some ongoing applications. Now, diamond is mostly known by its high hardness. Okay, it's the hardest material on Earth. It ranks 10 in the Mohs scale, and it is followed closely by silicon carbide or carborundum. It's also chemically inert, so you can't etch diamond with any liquid. Diamond has a very high Young modulus, which translates in a very high surface acoustic wave velocity. It has a high thermal conductivity. 5 times diamond conducts heat 5 times better than copper. It has a high band gap and breakdown field, so you can see here in comparison with other wide band gap materials that diamond excels them. It has a high electron mobility, and last but not least, it has a low dielectric constant. So all these properties altogether make diamond a very interesting material for many engineering applications. But now, how can we fabricate diamond? You have natural diamond and you have artificial diamond. And you can fabricate artificial diamond by high pressure, high temperature method or by chemical vapor deposition. Now, the high pressure, high temperature was the first method to be reported. So the first synthetic diamonds were produced in the early 1950s. And then later on, in 1955, GE researchers reported the successful growth of diamond in nature. And usually this is the typical reference that you find. It's 1955 Nature paper by Bondi. And an HPHD system simply tries to reproduce the formation of diamond inside the earth mantle, okay? So you have a press, basically, and in this press you have tiny seed crystals, and you have a high purity carbon source. And then as you apply a huge pressure, typically 5 gigapascal, and as you increase the temperature up to 1500 degrees, this metal will melt and will drag the carbon atoms from this carbon source towards the diamond seeds where they precipitate. Here you can see the inside of one of such systems. Here you see some diamonds that were fabricated with this method. After being cut and polished, they get these nice crystals. Okay, the yellow color comes from the impurity, the nitrogen impurity gives diamond this yellowish color. And these films are very perfect in terms of crystalline structure. They have a very high thermal conductivity. They are optically transparent, and they are available in sizes up to 10 times 10 square millimeters. And they find applications mostly in tribological area, like grinding discs. For cutting, here have a diamond saw. Here you have something that can be used to polish material also. All sort of, tools, diamond coated tools that you find, and also diamond suspensions for polishing of, for instance, hard metals. But you can also fabricate diamond by chemical vapor deposition, okay? This method was proposed in 1962 by Eversole. And initially, people didn't really believe that he had grown diamond. Why? Because he reported growing diamond here, okay, at low temperature and low pressure. And if you take a look at the phase diagram of carbon, this image tells you, as a function of the temperature and as a function of the pressure, what is the carbon allotrope that you expect to form. And under these pressures and temperatures, you expect graphite and not diamond. But yes, we can grow diamond by CVD. And there's a small trick. Here is the schematic of a CVD system. You have to start with a substrate. Okay, you always start with a substrate that can either be diamond or that has diamond seeds on it. And then you introduce gases, which are methane, typically, that contains carbon, and hydrogen. And you introduce mostly hydrogen, like 98, 99% of the gas is hydrogen. And then you have an activation, you have an energy that activates your molecules, which then the activated radicals flow to the substrate, and each carbon radical will bind to the diamond that is on the surface. And it will bind as graphite and as diamond, sp2 and sp3. But then you have excess atomic hydrogen that will etch away all the non-sp2, all the non-sp3 bonds. So in the end, you have like a growth, a deposition of sp2 and sp3 bonds, and then the excess atomic hydrogen cleans away or etches away all the non-sp3 bonds. And if you add dopants to the gas phase, you can also dope diamond. You can make it p-type with phosphorus, or you can make it n-type with boron. And depending on the activation, on the energy that you use to activate your species, you can classify them as hot filament CVD, where the activation is performed by this hot filament. Here you see it shining. It's a very simple system. You can scale it up quite easily, and you can coat complex 3D substrates, but you have a top filament temperature of around 2200 degrees C, so you have a low atomic hydrogen ratio, and you have low deposition rates, and you get contaminations with atoms from the filament. So this method is mostly used to coat tools. Now, microwave plasma CVD. The microwave energy is supplied by this magnetron. It travels through a waveguide, and then as it gets the chamber, it is reflected on the substrate, it's reflected back, and with resonance conditions, you create this plasma ball, okay, which is high energetic, so you have high growth rates, and you prevent contamination with atoms from the filament. However, since we are talking about resonance conditions, deposition area is limited by the wavelength of the radiation. So 4-inch for 2.45 gigahertz, and more or less 6-inch if you use 915 megahertz. Here you see a polycrystalline wafer deposit with this method. And finally, you have a linear antenna CVD. It's also a microwave, you also use microwave energy, but now you deliver this microwave energy using an array of antennas, of planar antennas. So you have the inner conductor, which is your coaxial antenna, but the outer conductor is replaced by the plasma. Okay, so you can get really large deposition areas simply by having these several arrays of these in parallel. You can reach 300 times 1000 millimeters square, so it's a huge area, and the films are very, very uniform. However, you have low deposition temperatures, which means, again, low growth rates. And also another word about the types of diamond films deposited by CVD. So I mentioned that we have a substrate, right? It can be either an HPHD diamond crystal or a diamond substrate. Now, if you have an HPHD crystal, you have homoepitaxial diamond films because you grow them on the same substrate. Here is one after deposition, after polishing, and these films have the best electrical properties. Okay, they even excel the ones of natural diamond, and they are ideal for electronic devices and thermal management. However, the area is limited to the area of the available HPHD crystals. Nevertheless, they find lots of commercial application for quantum optics, radiation detectors, and also monolithic diamond Raman lasers. Now, if you use a non-diamond substrate, you get heteroepitaxial diamond films, and you can use large area substrates like silicon carbide, gallium nitride, and then you overcome the problem of the small area. And the thermal conductivity can still be as high as 1800 watt per meter Kelvin. Now, they also have lots of commercial applications. For instance, windows, you have all these types of windows, X-ray, vacuum, laser, and microwave windows. Heat spreaders, you can buy these tiny diamond heat spreaders already with the electrodes on them. Submounts for disc lasers, and boron-doped diamond electrodes for water purification. And now a small word also about the CVD of heteropytaxial diamond. Now, you start with a substrate that is not diamond. So you have to seed it with diamond seeds, okay? So you can use a different variety of methods. And in the end, you have a substrate with lots of these seeds, okay? This is a seeded silicon substrate. And then you just put this substrate in the system and you grow diamond. You can use either of the methods I previously described, and this is a cross-section of the film after deposition. So you start with tiny diamond crystals, which start growing as columns following the Van der Drift growth model. And as a function of the crystal size, you can characterize them as micro, nano, or ultra nanocrystalline diamond films. Okay, and so this is all I have to say about how we grow diamond. And now, some applications. The earliest application that we tried in Aveiro was the fabrication of diamond-based SAW devices. Now, a surface acoustic wave device or SAW device is present in everyday electronic gadget. You have them as filters, delay lines, resonators, sensors, and more recently also as RFID tags. And they are very simple devices. They are a piezoelectric slab with some interdigitated transducer, which once, when you drive this IDT with an alternating voltage, you create this alternating field that creates a mechanical displacement because you have a piezoelectric substrate. And under resonance conditions, that is, if you meet the frequency of the interrogating signal and the spatial dimensions of the IDT, you generate a wavefront that just propagates all over the piezoelectric substrate. And we all know that, the geometric conditions are related with the pitch of the IDT and with the wavelength of the radiation, which in turn is related with the frequency of the interrogating signal and the velocity of propagation of the waves. And if you want to increase the frequency, you either have to decrease the pitch, which is not that, okay, it has some limits, or you have to choose materials with higher surface acoustic wave velocity, such as diamond, okay? But since diamond is not piezoelectric, you have to couple it with a piezoelectric material. And the typical approach is the growth of the piezoelectric layers on a single crystalline diamond substrate. And in Aveiro, we tried a different approach. We start with commercial devices and we simply coat them with diamond. And we've done that with a delay line. Here you have a die. Here you have the detail of the IDT. And we just seeded these dies and we deposited diamond by hot filament CVD for 1 hour. Here you have some photos of the films deposited on the IDT. So this one is not totally closed. And when we measure the S21 parameters, which are awful, because this is the S21 spectra of the uncoated dye, so we would expect a gain of minus 25 dBs. Here, even if we forget about this, the gain is below minus 60, and here the gain is below minus 50. So this approach was not the best. So we improved our seeding method, and we deposited again diamond, but now using a linear antenna CVD system. Here have the film, and these are the preliminary results we obtained, which are quite interesting, because you can see that the S21 parameters of the coated dye resemble the one of the bare dye. So we have almost no loss, only a tiny amount here, which is probably related with impedance mismatch induced by the diamond film. So this is currently undergoing. Another application is the passivation of silicon carbide devices and thermal management of gallium nitride HEMTs. And in this case, the diamond film is deposited directly on the surface of the device. Here, this is just a study where we evaluated the impact of the seeding suspension on the quality of the films. And we came to the conclusion that the seeding suspension plays a huge role. So seeding with 612 micron gives us a sharp Raman peak after 1 hour, whereas seeding with nanodiamond particles gives us a broad D and G band, so not really diamond yet. Also, for the thermal management of gallium nitride HEMTs, we started with a final HEMT dye. We coated it with diamond directly without any other treatment, and we got the device survived the deposition. At this moment, these are all the characteristics that we have. So we know that the device survived. We still don't know how the thermal management was improved. So this is also undergoing. Another topic is the fabrication of diamond transistors. So we just deposit P-type diamond films on silicon, and then we try to deposit high-K dielectrics like alumina, titanium oxide, and tantalum oxide on the surface of the diamond film by ALD. Here you see a cross-section, an FIB cross-section, and then higher resolution, same image here. So this is also a bit preliminary work. A very interesting topic that we are also evaluating is the use of diamond for the thermal management of devices, of fabricated devices, or at the package level. So in order to evaluate how diamond can really improve the thermal management, we started with power LEDs from Cree that have an aluminum nitride carrier. And we wondered what would happen if we replace this carrier with HPHT diamond or with CVD diamond. And we've done this with simulations with ANSYS. So we estimated what would be the junction temperature for different current ratings if you replace this carrier with low quality aluminum nitride or high quality and the two different types of diamond. And curiously, we can see that the temperature is more or less the same whether you use single crystal diamond or polycrystalline diamond. But these values themselves don't tell us much, so we use the black model to estimate the acceleration factor so that we can have an estimate of the improvement of replacing the aluminum nitride carrier with diamond. And this is what we got. So in this graph, I represent the acceleration factor when we consider a good aluminum nitride carrier, so 193 watt per meter Kelvin thermal conductivity. And we consider the two activation energies that we found in the literature that limit the aging effect. So you have either an activation energy of 1.05 EVs or 2.5 EVs. So these are the limiting values because we don't have the information from the manufacturer. And we calculated the acceleration factor for 350 milliamps, which is nominal current, and 800 milliamps. And in the worst case scenario, diamond will improve the lifetime between 15%, between 15% and 25% if operated at 350 milliamps, or 25% and 55% more or less if you operate the device at 800 milliamps. So this is what you expect to improve the lifetime if you replace a good quality aluminum nitride with diamond. But if the aluminum nitride has a lower quality, the lifetime will increase between 25% and 60% if operated at nominal current, or between 60% and maybe 90% if operated at 800 milliamps. So yes, you can really increase the lifetime of a carrier, of high power LED by replacing the carrier. But what if we use a diamond board instead of a carrier? So we started now again with the same diodes, but now we mounted these diodes on different boards. Two FR4 boards with and without thermal pads, one metal core PCB, one metal core printed circuit board, and a diamond board. And we mounted these boards on a heatsink, and we measured the evolution of the case temperature measured by this thermocouple as we applied current steps. And this is what we got. So on the left, you have a nominal current step. So you can see that the temperature increases a bit and then eventually it stabilizes. And on the right, you have the similar results, but now when you have a 700 milliamp current step. Again, the temperature doesn't tell you much, so again, we calculated the acceleration factor. And let's focus here, okay? So when we replace the metal core printed circuit board with diamond, if the activation energy is 1.05 and operated at nominal current, the acceleration factor is between 0.6 maybe and 0.12. So we increase the lifetime of the devices, of the LED, considerably by replacing this with diamond. Of course, if you operate them at 700 milliamps, the results are even more significant, because the acceleration factor is more or less between 0.12 and 0.012. So if whenever you have a high power LED and you mount it on a diamond board, you will increase its lifetime tremendously. Of course, you will not do it in a regular lamp, okay, because low cost is a must. But if you are talking about space applications, for instance, where both the lifetime as well as the weight and the volume of all your heat sinks and bulky stuff is also critical, then diamond can really play a role for the thermal management of these LEDs. And finally, a few words about biosensors. Now, a biosensor can simply be seen as a transducer, okay, which is any type of material, and on it we deposit an organic link layer and some receptor molecules. Okay, so these receptor molecules are such that they will only bind with target molecules. Okay, so these receptor molecules will give us the selectivity of the sensor. So whenever we immerse the sensor in a solution containing several molecules, it will only respond if you have the target molecules. And whenever you have a binding event here, the readout unit will record the change in the properties of the transducer material. And why is diamond interesting? Because besides being biocompatible, diamond creates very strong covalent bonds between the surface of the diamond and the organic link layer, meaning that you get robust sensors. And the target molecules can be basically anything you want, from antibodies to detect diseases, to antigens, to DNA, if you want to detect genetic conditions, and even chemical compounds. And the interrogation itself can be, you can interrogate your sensor by monitoring its electronic properties, its optical properties, or also its acoustic properties. And here in Aveiro we are trying electronic interrogation as well as optical interrogation. So for the optical interrogation, we are using optical fibers. So we remove the protective polymer, we see them, and we grow diamond on them. And this is what you have. This is a study where, again, we evaluated the impact of sealing, using different sealing suspensions on the quality of the films. So these fibers broke, okay, they are very brittle. It's not that easy to handle them. This one is totally covered. Here you see the morphology of the film, which is a bit different, and then a cross section, okay, showing that the film is totally closed and it really covers the optical fiber. And finally, the Raman spectrum. Okay, so again, showing that sealing with 612 has a very sharp diamond peak.
Joanna,
And
5
now the
minutes.
second step. Okay, thank you. And now we are using this same concept, and we are trying to fabricate Fab-Ripper interferometers, okay, just by growing here diamond, and the diamond film will behave as the resonance cavity. So you have a reflection here at the interface between the fiber and the diamond, and the second one between the diamond and the analyte solution. So we hope that whenever we have a binding event, there will be a change in the refractive index that will translate in a change in the reflected spectra. So currently, we are just coating the Fab-Ripper interferometers. And finally, using electrical interrogation for biosensors. So we started with this is a recent collaboration. So my colleagues in Coimbra, they are using these gold electrodes, gold substrates, to measure the low frequency signals of cells but they found out that these gold electrodes are very noisy. You know, low frequency noise, it's a pain. So we are trying to replace these with diamond. And here you see two different images. Now, why diamond? Because first, it's biocompatible, so you can grow the cells directly on diamond, and cells love these pattern structures. So the next step is to grow cells here. What we've done so far, we just measured very simply we've made the impedance measurements, and we found that the diamond electrodes behave better than the gold electrodes, and that are less noisier. So we expect this work to also give some good results, but like I told you, it's just preliminary. And so this work has been supported mostly by our Portuguese funding agency, as well as by the Telecommunications Institute. And now I thank you all for your attention, and I'm available to answer a few questions if I still have time.